So we're now going to introduce this notion of improper integrals. This is our first case. An improper integral is an integral where either the upper or the lower or potentially both. We'll cover the other scenarios. There are three scenarios. This is the first. Upper limit of integration or the lower limit of integration or potentially both limits of integration are either positive or negative infinity. If the limits of integration are one or the other of the infinities, that's called an improper integral. It's not really, there's nothing improper about it, it's just that's the name we call it. Now, each of these is handled with a limit statement, and here's why. What we're actually finding is this. Let's suppose, I'm going to pick a picture out of the blue sky. Suppose I just have that's my graph of the function y equals f of x. And let's just pick a number here. Let's suppose a is right here. Again, it doesn't matter what this is. A can be any finite value. What do we mean? One of the interpretations, let's use for this purposes of this discussion, let's use the interpretation of area under the curve. So all the interpretations in this discussion will be area under the curve. What we mean is the area starting at A on the left. But on the right, the question is, where do you stop? Where do you stop accumulating area? You start at A and you accumulate more and more area. The question is, where do you stop? And the answer is, you don't stop anywhere. You continue on without, and the key word is without a boundary. Boundary and is always a boundary and unbounded, bounded and unbounded is always related with infinity somehow in mathematics. This is an unbounded region, and it turns out that when we do this, if we do this computation for this sort of a structure, our final answer actually would be infinity. What we're saying is that area is infinite. There is no finite number that corresponds to that area. Now, another possibility would be this. You might think, well, that's always going to happen. Well, not necessarily. Because another possibility might be something like this. This curve might approach a horizontal asymptote. Now, let's suppose, there's nothing that requires A to be positive or negative or zero. A can be anywhere. So just to illustrate the point, I'm going to choose A over here to the left. You may choose A to be anywhere on the x-axis. That's not the important piece. And now the question is, as you start at A and you accumulate the area, again, the question is, where do you stop in this accumulation procedure? Where is the boundary? And what this says is there is no boundary. And even though it might seem at this stage of the game, from your side of the camera, it might seem counterintuitive, it turns out that even though this region is unbounded, it has no boundary, the area of this region could be finite. The key is the way we define what area represents. And so one possibility is this could work out to be infinity. Another possibility is this could work out to be finite. But the point is, we start at some finite value A, and you accumulate area, and you never stop. That's one of the interpretations. If we use area under the curve, that's how we interpret this. So this could work out to be infinity. This could work out to be a finite value. Now, the question is, well, how might we find this area? Well, here's a way to think of it. Let's go back to this picture. And let's suppose that this area actually is a finite number. Here's a way to think of it. Suppose I pick a value. Let's call it, I'm going to pick a number out of the blue. Here, boom, and call that B number 1. And we accumulate the area between A and B number 1. Is it clear that area is an approximation of the total area we want to find? This is going to sound very similar to the area problems we did way back in Calculus 1. This approximation, this area we have is an approximation of the area we want. It's just a bad approximation. Well, how do you make the approximation better? You choose a larger B. If B number 2 is larger, now we're talking about all of that area. Let's get rid of this. Now we're talking about all this area. That's a better approximation. If I choose a larger value for B, in fact, if I choose, again, this is supposed to be asymptotic. If you choose a very large value for b, maybe b3 is further out, then you're getting a better approximation. And as b gets larger and larger and larger, the approximation gets better and better and better. That's the notion of this limit. And so what we say is, anytime we have the upper limit of integration is infinity, here's how this works. This is the definition, or we will use this as the definition. This is the limit as b. Now notice, I will always do this. This is the standard procedure. I will always do this. Lower limits of integration I'm going to call A. Upper limits of integration I'm going to call B. Not because it's required, but because that's the way people do it. And so, limit as B goes to infinity as the upper limit of integration. Because look, this region is the integral from A to B1. This region is the integral from A to B2. This region is the integral from A to B3. And as B gets larger and larger and larger, as B gets larger and larger and larger, the integral from A to B, that's what we mean by this expression. Whenever you have an improper integral, you replace it with a limit statement and a proper integral where A and B are finite values. You evaluate that just the way you've always evaluated, using whatever technique of integration you need to evaluate that expression. And then once you get that expression, you're going to have this is a definite integral, evaluate at the top minus evaluate at the bottom, and then you evaluate this limit. That's the procedure. Replace with a limit statement, evaluate the integral, substitute the limits, and then find the limit. All right? Replace with a limit statement, evaluate the integral, substitute the limits of integration, and then the last thing is you evaluate this limit. You work from the inside out. And so what we'll do is we'll go through several examples of this to make sure you have the feel. Now, before we leave this bit, I want to talk about the other potential scenarios. We've talked about this. So this is the limit as b, the upper limit of integration goes to infinity, of the integral from a to b. I need a dx in here. My differentials are missing. All right? Well, you could also have negative infinity to b. That would be the same picture, but you'd have to flop it around to the other side. Now you're talking about this kind of a picture where you're receding out the x-axis this way. The left limit of integration, negative infinity. The right limit of integration is now some value b, and now you're accumulating this area. But it's the same notion. The difference here is this is now, you replace this with a limit statement. This is the limit as, again, when it's the upper limit, I will use b. When it's the lower limit, I will always use a. And this is going to negative infinity of the integral from a to b. All right? So you could have the upper limit of integration. You have the limit for the upper limit for the upper value here. You have the lower limit of integration. You have the limit for the lower value. And then you could also have this, negative infinity over infinity f of x dx. And the way you do this is recall from Calc 1, one of the properties of Calculus 1 is that this integral that if you have the integral from a to b, you can split this at any convenient value. A to B, going from A to C, then from C to B. And so we may split this at any convenient value. We may rewrite this as negative infinity to C, and then C to positive infinity. And so if you have infinities at both ends, you change it into one like this, and then one like this, and you split this infinity at any convenient value. C, you may choose it to be any finite value you like. And so we'll do several examples of this, and it will be very straightforward.